Hey, AP Stats, here we go with section 7.2 on sample proportions. I want you to put a big giant p hat up here because this whole section is about the sampling distribution for proportions, sample proportions. So when we find out that this thing is a normal distribution later on, the mean will be of p hats because the math that we're doing to the sample is to find a proportion. Okay, for the question, what year did Columbus discover America? A Gallup poll found that 210 out of 501 American teens aged 13 to 17, 210 out of 501 knew that the answer was 1492 when Columbus sailed across the ocean. And so when I started teaching this class 20 years ago, we all thought it was really odd that people didn't know this date, but more and more often I'm finding that social studies students don't kind of have these dates memorized. And that I think the reason for that is social studies has moved on more towards, like comparing things and learning from things rather than memorizing dates, which is probably a good thing. Anyway, this thing that we found, 210 out of 501, that is a sample proportion. Okay, remember all the way back to chapter 1 where you could have categorical data or quantitative data. Well, this is categorical data. Did you know what year this is? Yes or no. There's just two categories. So this is an amount of yeses out of 501. So it doesn't make sense to take an average or find a Q1 or anything like that with this information. So it goes like this. P hat out of this sample is 210 out of 501, or p hat is equal to 0.42. All right, the sampling distribution of p hat. Now keep in mind the population parameter would be a proportion, but it would be capital P. And this p hat represents the proportion we get out of a sample. To find out how good a statistic, remember the statistics are the mathy things we do to samples. So this mathy thing was take 210, put it out of 501, and make it a proportion, like a percentage. That's the math we did there. So the statistic is p hat. A statistic like p hat, to find out how good it is at estimating a parameter. Parameter is the math that we're doing to the population. So I'm going to put a capital P here. That's the proportion from the population. We have to investigate this following question, and this is what this whole chapter is about, the definition of a sampling distribution, so that we can answer this question. What would happen if we took many samples? You guys saw with our activity where we did the random integer and we counted the evens, that when we had a larger sample size, we had a distribution that had a smaller standard deviation. And so if we take all of the samples and the sample size is as big as 501, we're probably going to have a small standard deviation. Recall that the definition of a sampling distribution of p hat for a sample size of 501 would go like this. It's the distribution of every possible p hat from every possible sample out of 501 American teens. That's what a sampling distribution is. This is why we study it, so that when we do get something like this, we have a feeling for how close we think that should be. Okay, let's keep in mind that p hat, the way we got this is the number of successes out of the size of the sample, or we're going to call it x over n, right? So that p hat would be x the number of successes out of n the number of trials. That's how we find a p hat in the first place. Well, we can say that p hat and x, the numerator here, both of those are going to vary in repeated samples of 501 teenagers. N doesn't because it's 501. So they are, in fact, you ready for this? From last chapter, both p hat and x in the numerator are random variables. In fact, since x, that numerator, is a count of successes out of 501 trials, we can even say that x, let's see, that's a set number of trials. It's a yes or no question. The probability is the same every time because there is a probability out there of kids who know this. This is, in fact, a binomial random variable. Hello. And look what I wrote after that. You did not see that coming. P hat being x over n. X is the count of the number of successes out of a set number of trials. That's a binomial random variable. That's a constant underneath it, but that's a binomial random variable in that numerator. Let's go to page 2 and find out more about what we're going to do from the last chapter's binomial stuff with this p hat sampling distribution, the collection of every possible sample of the same size. So for p hat equals x over n, x is a discrete random variable. Not only that, as long as the population is at least 10 times bigger than the sample size, x actually has a binomial distribution, which is pretty much what I said on the last page. But I do enjoy saying this stuff with drama. So, although p hat does not have a binomial distribution, because once you divide by n, it actually turns into a continuous random variable. And so we'll have to represent the actual p hat distribution with some kind of a density curve. Probably a normal curve, wouldn't you think? But if we're just focusing on the x, though, that numerator, let me write it up here again. The p hat that we're focusing on has a numerator that is a binomial random variable. So for x, from that formula, we know this. The mean of the x would be n times p, and the standard deviation of the x would be the square root of n times p times q. Those are from last chapter. That's because this is a binomial distribution that goes n comma p, right? That's the mean of a binomial random variable. That's the standard deviation of a binomial random variable. And that's why we learned that stuff last chapter. But we need a mean and standard deviation for our sampling distribution for p hat, not just x. And yeah, I see it. Okay, it should have been the word r. I don't make fun of you guys. Now, remember from chapter 6, if you multiply every data value by a constant, see, we have rules for this. Look at what's going on. That's a binomial random variable. Isn't this really x times 1 over n? Because n is a set number, like in that one we talked about, 501. So this is a constant. So I'm actually multiplying every x value by the constant, 1 over n. Remember from chapter 6, if you multiply every data value by a constant, this is how it affects the mean and the standard deviation. The mean of b times x ended up being b times the mean of x. You just multiplied the mean by whatever number you were multiplying by. And the standard deviation of b times x ended up being the standard deviation times b. So we learned, remember they were called linear transformations. And I'm not adding anything here, I'm multiplying. And you definitely changed the mean by multiplying, and you changed the standard deviation by multiplying. So we have a mean and standard deviation for the distribution of all p hats. Let's consider b in this scenario here to be 1 over n from the top. And since n is a constant, like for the example that we did on the other page, 501, we can definitely do this. The mean of the p hats, the center of the sampling distribution for p hat, is like the mean of 1 over n times x. So I can just multiply that 1 over n times the mean of x. And the mean of x is right here. Whoops, where is it at? It's right here, n times p. So look, that's going to be 1 over n times what I just pointed out, n times p, because that's the mean of x, right? N times p in a binomial random variable. Well, that 1 over n cancels with that n, and so we have the mean of the p hat sampling distribution is the population proportion p. And didn't we learn in the last notes that if the center of the sampling distribution is actually at the parameter we're looking to estimate, we can call this statistic, that one right up there at the top, an unbiased estimator. And now the standard deviation of p hats. Okay, well, that's the standard deviation of 1 over n times x. And so there's your 1 over n, and we learned that we can multiply the standard deviation by the constant. So it's 1 over n times, instead of the standard deviation, I'm going to write the formula from up here, the square root of n times p times q. Okay, I would like this n to cancel with that one, but that's in a square root sign. I can't do that. So here's what I'm going to do. I'm going to square it and shove it under the square root sign. Watch. This becomes one fraction underneath the square root sign of n times p times q over n squared. If I wanted to simplify that, wouldn't I take the n squared and put it out like this, right? So I just unsimplified a radical so that I can cancel that n, and look what we get as a standard deviation formula for for the sampling distribution of p hats. That n is gone. It's pq over just one n because one of them canceled. All right. So I think on our next page, I'm actually going to write these out, but I just would like to put them down at the bottom. You may write them a couple of times, but it's not going to hurt you. The mean of the sampling distribution of p hats is the population proportion p, and the standard deviation of the p hats we now know is the square root of p times q over n. That's the center and the spread of the sampling distribution for p hats. Let's go to page 3. Now you got formulas. You love formulas. You guys love formulas. Okay, so definition. I'm going to write them one more time, but here's where they are. So this is for the sampling distribution of p hat, the collection of every possible p hat from every sample of the same size, out of a size n. The following are the mean and the standard deviation. The mu of p hats is equal to the population proportion p, making it an unbiased estimator. By the way, we should probably we'll write that down. Making p hat an unbiased estimator. I said this in class. I'm not a big fan of this definition, that unbiased estimator thing. It's just saying that the center of your sampling distribution is where it's supposed to be. But it comes up often, and I know it comes up on the AP exam in like a multiple choice question. The standard deviation of p hats is the square root of p times q over n. Okay? It's worth writing down that since the mean, oh my God, it's this right here. I really should have looked ahead. I'm so dumb. Since the mean of the sampling distribution of p hat is in fact the population proportion p, by definition, p hat is an unbiased estimator. Sorry about that, people. I just wasted your time. Didn't need to do that. Unbiased estimator for the population proportion p. Okay, now let's say one more thing about these formulas here. All right, since n is in the denominator of the formula, standard deviation is the square root of p times q over n. Didn't we notice that if you put in a larger sample size, that the standard deviation gets smaller? Imagine putting bigger numbers in for n. Wouldn't that make this number smaller? Right? We saw that in our activity at the beginning of chapter 7 here. Since n is in the denominator, as the sample size n gets larger, that means that the spread of this sampling distribution for p hat gets smaller. In fact, we could put kind of a ratio to it. To cut the spread in half, to cut the standard deviation of this distribution in half, you would have to make the sample size 4 times as big. Because look, if you put a 4 in here and bring it out under the square root, it's going to turn into a 2 in the denominator, right? So to cut it in half, you got to put a 4 in there. So if I wanted to cut it in like 1/4 as big, like I had this big standard deviation, sampling distribution, standard deviation, I want it real small so that I know when I take my one sample, it's going to be real close. If I wanted to cut the standard deviation and divide it by 4, I would have to make this 16 times as big, so that when you take the square root of 16, it becomes a 4 in the denominator. Okay, the two conditions that follow the sampling distribution of p hat. 1, you can only use this formula for p hat if you have a binomial setting, because it came from the binomial setting on the other page. So the population's got to be at least 10 times the size of the sample. Otherwise, you violate the independence condition by sampling without replacement of the binomial setting. Remember checking your bins? If you check your bins and you're sampling without replacement, you're supposed to say that violates the independence condition. But we decided that if the sample was less than 10%, this is another way of saying it, is that the sample is less than 10% of the population, we're okay with the independence condition, we're okay with the binomial setting, and now that we use the binomial setting to come up with this formula, that has to be true, that 10 times, that 10% condition has to be true for us to use this formula. We have no business using that formula if the sample size is bigger than 10% of the population. Now, like we did in the binomial chapter, if n times p is greater than or equal to 10, and n times q is also greater than or equal to 10, we will use the normal distribution as an approximation for our sampling distribution. That way we can find z-scores, or we could use the normal CDF to answer probability questions, but also later on in chapter 8, we're going to build new formulas for a new concept. And so we definitely have to have the normal curve for that, not just binomial CDFs. This works best, by the way, when P, the population proportion, is closer to 0.5 than 0 or 1, because when it's 0.5, if P is 0.5, that would be the highest bar, and then they drop off in both directions. And so it's almost like it's a symmetric graph anyway. But that's when P is equal to 0.5. But if P is equal to like 0.1, then what happens is you're likely to get a 0 or a 0.1, and then look what happens with the rest of this histogram. It's heavily skewed right. And so this one turns into a normal curve a lot quicker than this one as you make the sample size bigger. Okay, let's go to the next page and look at a couple examples. Now that we've got all this theory and formulas, let's do something with them.